Okay, students, now we'll see the disadvantages of delta modulation. Now, what is the step size? The step size is delta. So, what is the maximum quantization error? The maximum quantization error is which is delta by 2. So, delta here is now the maximum quantization error step size by 2, delta by 2, delta is for 10, 10 by 2 is 5. So, this is the maximum quantization error. So, the maximum quantization error which is equal to 5. But here this is maximum itself is 5, but this is out of this particular range. That's why the disadvantage is this step size we are calculated based on maximum slope of the message signal, which is suitable for the larger amplitudes and which is not suitable for the smaller amplitudes. Okay, then you understand or not? So actually the quantization error, a maximum allowable value is 5, but here this is 0.8, good, but this is 9.5. But here you get a large quantization error for small amplitudes, now small quantization error for larger amplitudes. Therefore, what is I am saying, this step size choosable value, now how you are selecting this step size which is good for this larger amplitudes, but the step size what you are choosing which is not suitable for the smaller amplitude, but this is also the information. Now at this particular information you are introducing an error of 9.5 means there is a large deviation you are biforcely introducing and you will get the unwanted signal or a distorted signal. Okay, so this step size selection is calculated based on the maximum slope of the message signal which is good for the larger amplitudes of the message signal, which is not suitable for the smaller amplitudes of the message signal. That is the problem in the case of delta modulation. Understand or not? Okay. Sir, then the students are asking that, sir, then how to overcome this? Now you tell me, now this step size, whatever we are using so far, PCM, DPCM, delta modulation, all these things are, this step size is fixed. This step size value is fixed value. This step size is fixed. Right, this step size is fixed and it is calculated based on this step size is fixed and is calculated based on maximum slope of the message signal. This is called as uniform step size. Now, this uniform step size which is not suitable for larger amplitudes, for smaller amplitude, which is good for the larger amplitudes. Therefore, to overcome that particular problem, now this step size is varied. The step size is varied and it is calculated, and this step size is varied and is uniformly, and it is continuously changing. Based on continuously changing with respect to message signal, with respect to or slope of the message signal, with respect to slope of the message signal. This step size is varied and it is not fixed. It is varied and it is continuously changing with respect to slope of the message signal, which is very good for us. Now this is called as non-uniform quantization. This is uniform quantization. This process is called as uniform quantization, and this process is called as non-uniform quantization. This step size is fixed uniform quantization, not fixed is non-uniform quantization. Now this variable step size, now this is the step size is varied here. Now here step size is variable. Now here step size is fixed. Now this is PCM, DPCM, delta modulation. Now this step size is variable. Now this is called as an adaptive delta modulation. Adaptive. Now this is delta modulation. This is adaptive delta modulation. Okay. Now this is not at all a easy technique, because message signal is a continuous wave signal, sinusoidal signal whose slope is continuously varying with respect to time, and for every continuous variation of the message signal, it is very difficult to design continuous step size variation is somewhat difficult. Okay, but we will take that one. Now see here, this is a message signal. This is a message signal m of t. So here now the step size is changed. Now this is delta 1, delta 2, delta 3, delta 4, delta 5, delta 6, delta 7, delta 8, delta 9. Now where the message signal slope is changing, now where the step size is also continuously changing, now this is called as adaptive delta modulation. Understand or not? Now where the step size is continuously changing according to the slope of the message signal, where step size is fixed and is calculated based on maximum slope of the message signal, is a uniform step size. Okay, but this adaptable technique is not an easy technique. So this is generally how the practical implementation is. It will take over a duration of time. Let us take from t1 to t2 seconds. Now over this duration of time, slope is more. So here step size is also more. Like that we can introduce a technique like this. Now over a duration of t2 to t3, slope is less. Slope is less. Now step size is also less. Slope is decreasing. Now step size is also decreases. Now during the duration of t2 to t3, slope is less. Now step size is also less. Now like that over a duration we can consider, and we are increasing the slopes or we are decreasing the slopes. Okay. Now this is the technique of the adaptive delta modulation, where slope is continuously changing and a message signal is also continuously changing. Therefore step size is also continuously changing. Not a easy technique, but this is a somewhat a practical implementation. More step size, more delta, less step size, less delta. So here the step size is proportional to slope of the message signal. This is the technique of an adaptable technique, and these are the remaining uniform quantization techniques. Okay, no doubt. Now we'll solve the problems of delta modulation, the classroom workbook problems. Now in a classroom workbook problem, question number 1. What is the question number 1? The input to a delta modulator, is m of t equal to 10 cos 2 pi into 10 power 3 into t, and bitrate is 50 kilobits per second. 50 kilobits per second. Determine the optimum value of the step size. See here. Now this is m of t, which is equal to am cos 2 pi fm into t. Am cos 2 pi fm into t. Now therefore, the optimum value of the step size. Now in the question he is asking optimum value of the step size. The optimum value of the step size, which is nothing but now the slope of the reconstructed signal and slope of the original signal, both are same, then there is no error. Optimum means no error. So he is asking determine the optimum value of the step size. Now here you know that in delta modulation, bit rate, which is equal to sampling rate. So this is 50 kilobits per second, which is nothing but 50 kilo samples per second. So therefore this is 50 kilo samples per second into this optimum step size, which is equal to 2 pi fm 1 kilohertz am 10 volts. Therefore the optimum step size, which is equal to 2 pi into 1k into 10 by 50 k cancel. Therefore the optimum step size, which is equal to 2 pi by 5 volts. This is question number 1. Right? Now question number 2. The input to a delta modulator, the question number 2 is in classroom workbook question number 2. The input to a delta modulator, which is m of t, which is equal to 5 sine 2 pi into 10 power 3 into t. The step size is 0.314 volt. Determine the pulse rate which will prevent the distortion. Now he is asking to avoid the distortion. This is am cos or sine, not a problem, 2 pi fm into t. Now to avoid the distortion, now this is which is equal to 2 pi fm am. To avoid the distortion, the slope of the reconstructed signal, slope of the message signal will be same. So the peak amplitude of the pulse distortion, which is equal to 2 pi fm into am by the optimum step size. Now which is equal to 2 pi fm, which is 1 kilohertz. Now amplitude of the message signal, which is equal to 5 volts, by the optimum step size, which is equal to 0.314 volts. Now this is the pulse rate. Now this is the sampling rate, and this is the bit rate. All are same. The sampling rate pulse rate, bit rate, all are same, which is equal to 2 pi by 3.14 into 10 power minus 1 into 1 kilo into 5. Now therefore, this is 3.14, this is cancelled. Now which is equal to 5 into 10, 10 into 10, 100 kilo pulses per second, which is nothing but the pulse rate. Because in delta modulation, one sample, which is nothing but one pulse, which is nothing but one bit. One sample, one pulse, one bit. So sampling rate, pulse rate, bit rate, all are same. Sample per second, pulse per second, bits per second. Okay, this is question number 2. This is question number 1. Now question number 3. The input to a delta modulator is a sinusoidal signal. The input to a delta modulator is a sinusoidal signal. Now whose frequencies are varies from 200 Hz to 4000 Hz. The input to a delta modulator is a sinusoidal signal whose frequencies each varies from 200 Hz to 4000 Hz. The signal is sampled 8 times the Nyquist rate. The sampling rate is 8 times the Nyquist rate. The step size is 0.314 volts. Determine the peak amplitude of the message signal which will prevent the distortion at a frequency of 800 Hz. Okay, now first we will do. Now what is the Nyquist rate? The minimum sampling rate, which is called as Nyquist rate, which is equal to 2 into omega is 4 kilo. Therefore, the Nyquist rate, which is equal to 8 kilo samples per second. Now the sampling rate, which is 8 times the Nyquist rate. 8 times the Nyquist rate, which is equal to 8 kilo, which is equal to 64 kilo samples per second. 64 kilo samples per second. Now this is the sampling rate. Now what he is asking is determine peak amplitude of the message signal which will prevent all the distortions, means this is the optimum step size and no error. And in the question is asking peak amplitude of the message signal. This is the peak amplitude of the message signal AM, which is equal to, what is optimum step size is already given, 0.314, and sampling rate we are calculating 64 kilo, which is equal to 2 pi. Now FM, where he is asking to find FM at, now determine the optimum step size at a message signal frequency of 800 Hz. He is asking at 800 Hz. So at 800 Hz, what is the peak amplitude of the message signal? So what is the peak amplitude of the message signal? 0.314 into 64K by 2 pi into 800. This is the peak amplitude of the message signal. Question number 3. Now this is the question number 4. The input to a delta modulator having a step size of 0.628 volts. The input to a delta modulator is a sine wave, with amplitude EM with frequency FM. With amplitude EM with frequency FM, and the sampling frequency is 40 kilohertz. Sampling frequency is 40 kilohertz. Now the sampling frequency, which is equal to sampling rate, which is equal to 40 kilo samples per second. Sampling frequency, which is equal to sampling rate, which is equal to 40 kilo samples per second. Okay. So what he is asking is the combination of EM and the combination of FM which will prevent slope overload distortion. The combination of EM, the combination of FM, such that the slope over distortions will occur. The slope over distortions will taking place. So this is the condition to occur slope overload distortion. Is it right or not? This is the condition. This is the condition to occur slope overload error. This is the condition to occur slope overload error. Now this is the step size 0.628. Now the sampling rate is 40 kilo less than 2 pi FM. What is FM? FM we have to be calculated, and EM which is calculated. This condition should satisfy, then only you can have a slope overload distortion. Now in the options, the different values of AM and FM is given. 8 kilohertz and 0.3 volts, and 4 kilohertz and 1.5 volts, 2 kilohertz and 1.5 volts, 1 kilohertz and 3 volts. Now which combination if you are substituting here such that this condition is satisfied? So these are the combination such that now this equation is satisfying. This is the peak amplitude of the message signal, frequency of the message signal such that you have an error. That error is nothing but the slope overload error. Okay, no doubt. Now see here, this is the PCM. Now in pulse code modulation, this is a uniform quantizer and the quantization error varies between minus delta by 2 to plus delta by 2. You know that? Now this is the quantization error which is varies from minus delta by 2 to plus delta by 2. Minus delta by 2 to plus delta by 2. Now this is a uniform quantizer. Therefore, the probability density function of that particular quantizer is the quantization error which is uniform and which is from minus delta by 2 to plus delta by 2. And a uniform quantization means, now what is the probability density function? 1 by b minus a, 1 by delta by 2 minus of minus delta by 2, which is equal to 1 by 2 delta by 2, therefore 1 by delta it is. Right? Now this is the quantization error which is uniformly distributed. This is the uniform distribution, you know the distributions and all these things, right? So now what is the quantization noise power? The quantization noise power which is equal to expectation of power is nothing but a mean square value, expectation of x square, which is equal to integral minus infinity to infinity x square fx of x dx. Now similarly here, which is minus delta by 2 to plus delta by 2 x square fx of x is 1 by delta dx. Therefore 1 by delta, now this is x cube by 3 x cube over the limits minus delta by 2 to plus delta by 2. Therefore the quantization noise power or a quantization error power which is equal to 1 by 3 delta into delta cube by 8 minus minus plus delta cube by 8. Therefore which is nothing but 2 delta cube by 8 into 3 into delta. So this is delta square by 12. You know this is the quantization noise power of a PCM system which we already solved the problem. Now in the same manner, can you find in delta modulation? This is a delta modulation. In delta modulation, the quantization levels are only two, whether it is minus delta or whether it is plus delta. So this is also the uniform distribution. This is the quantization noise power. The quantization are uniformly distributed in the interval of minus delta to plus delta. Now What is the probability density function? Uniform distribution function, which is nothing but 1 by b minus a 1 by 2 delta, right? Now similarly, can you find the quantization noise power in the same manner? So the quantization noise power of a delta modulation is, which is nothing but mean square value, minus delta 2 plus delta x square fx of x dx. Therefore, which is nothing but fx of x minus delta 2 plus delta x square fx of x is 1 by 2 delta into dx, which is equal to 1 by 2 delta x cube by 3. Now over the limits minus delta 2 plus delta. Now which is nothing but 1 by 3 into 2 delta, which is delta cube minus of minus delta cube, which is equal to 2 delta cube. This 2 cancel. Therefore, this is delta square by 3, which is the quantization noise power of a delta modulation. So here sometimes the questions are asking quantization noise power of PCM, which we already solved in PCM classroom workbook problems, but a quantization noise power in all your delta modulation problems, classroom workbook question 1, question 2, question 3, you can also solve the quantization noise power of a delta modulation. This is the formula. Okay, clear or not? So now you tell me, what is the signal to quantization noise ratio? This is the signal to quantization noise ratio of a PCM system, which is nothing but 3 by 2 into L square, or 3 by 2 into 2 power 2n. Now the signal to quantization noise ratio of a delta modulation, which is nothing but 3 by 8 pi square into fs cube by fm square into capital Fm. Now fs is sampling frequency. Fs is sampling frequency. Small fm is message signal frequency. Message signal frequency. F capital M is cutoff frequency of message signal. Sorry, F capital M, cutoff frequency of low pass filter. Okay, so if cutoff frequency of the filter is not given, generally the cutoff frequency of the filter, which will be the same as that of the message signal frequency, band limiting frequency is Fm. So if cutoff frequency of the filter, which is equal to Fm, the signal to quantization noise ratio of delta modulation is 3 by 8 pi square. Now this both are same, therefore Fs by F small m whole cube. Now why I am giving this comparison? Because in our classroom workbook there is question number 5. This is question number 5 in our classroom workbook delta modulation problems. Now there is a question like this. Bit rate in a delta modulation is, what is the question is given is, bit rate in a delta modulation is 5 kilo bits, bit rate in a delta modulation is 64 kilo bits per second. And the input signal bandwidth, the message signal bandwidth, m of t bandwidth, which is nothing but omega, which is nothing but Fm, which is given as 4 kilohertz. And here cutoff frequency of the filter is not given. If cutoff frequency of the filter is not given, treat it now capital M, which is equal to small m. Cutoff frequency of the filter will be same as that of the message signal frequency. When cutoff frequency of the filter is equal to the message signal frequency, now he is asking what is the signal to quantization noise ratio of a delta modulation. The signal to quantization noise ratio of a delta modulation is 3 by 8 pi square into sampling frequency is in delta modulation, you know, bit rate which is equal to sampling rate which is equal to sampling frequency, all are same. Therefore, which is 64 kilo by FM, frequency of the message signal. What is the frequency of the message signal which is given? 4 kilo whole cube. Kilo cancel, which is equal to 3 by 8 pi square into 64 by 4, which is nothing but 16 whole cube. Now which is equal to 3 by 8 pi square into 16 cube, which is the signal to quantization noise ratio of a delta modulation. If he is asking in terms of dB, then this value take it in terms of logarithm after simplifying calculation part 10 log, then you can get the signal to quantization noise ratio in terms of dB. Okay, no doubt. If m of t which is equal to phi t, and if m of t equal to phi t and sampling rate is 5000 samples per second and sampling rate is 5000 samples per second, determine step size. Determine step size. Now, whatever the problem what we have solved so far is m of t is not this. Now, whatever we are solving, now in all the problems, message signal is a sinusoidal signal. Am I right? Not. It is a continuous wave signal. Now, whatever the problems you are solving, all that formulas and all these things are only for sinusoidal signal. But this is like m of t, which is equal to at, is a linearly varying signal, which is nothing but a ramp signal with a slope of a, right? And now if it is a ramp signal, then the slope of the reconstructed signal, which will be same as that of slope of the message signal. The slope of the reconstructed signal, which is equal to same as the slope of the message signal, which is nothing but delta by ts, which is equal to slope of the reconstructed signal, which is equal to slope of the message signal, delta by ts, which is equal to d by dt of m of t. D by dt of m of t is at. Now, the slope of the reconstructed signal, which is equal to a into t. Now, without any error, right? Now, without distortion, without error. So, what he is asking? Optimum step size. Now, this is delta into 1 by ts is nothing but sampling rate, which is equal to a is slope of message signal. Slope of the message signal, here message signal. So, what is the optimum step size? The optimum step size is nothing but slope of message signal by sampling rate. Slope of message signal is 5. Sampling rate is 5 kilo samples per second. Now, which is nothing but 5 cancel, which is 1 millivolt. Now, question number 7. If m of t, which is nothing but 125 into t, u of t minus u of t minus 1 plus 250 minus 125 into t into u of t minus 1 minus u of t minus 2. This is m of t. And sampling rate is 32 kilo samples per second. This is question number 7. Okay. And sampling rate is 32 kilo samples per second. Now he is asking to determine optimum step size. He is asking to determine the optimum step size. Okay. Now first of all, this signal you need to find what is the signal, given signal, and step size is how much. Okay. Question number 7. Now let us see first u of t minus u of t minus 1. This is u of t minus, this is u of t minus u of t minus 1. Now what is u of t minus 1? Now u of t minus 1, which is nothing but, this is u of t minus 1. Now u of t minus u of t minus 1, which is nothing but u of t minus u of t minus 1. Now this is from 0 to infinity, and this is from 1 to infinity. This is subtraction is possible. This is only 0 to 1. And now this is u of t minus u of t minus 1 multiplied with 1 by t. Sorry, 125 into t. So this is a ramp signal with a slope of 125 into t. Right? Now this is a ramp signal now with a slope of 125. So such that if you want a slope of 125 a into t, therefore now the signal will be converted like this. This is 125 now, I think. Such that what happened? Now see here, this is the line. Now I am taking, this is 0, 0. Now here if I am taking 1 comma 125. Now see the slope, 125 minus 0 by 1 minus 0, which is equal to 125, linearly varying with respect to time. So therefore this is now 125 into t. Okay. Now this is added with u of t minus 1. U of t minus 1 is, this is 1 minus u of t minus 1. What is u of t minus 1? Now this is u of t minus 1 and this is u of t minus 2. This is u of t minus 1 minus u of t minus 2. U of t minus 1 and u of t minus 2. 1, 2. U of t minus 1 minus u of t minus 2. Now this is multiplied with, now this is a negative slope. Slope is negative, therefore this is falling. Between 1 to 2. This is a negative slope with minus 125t plus 250. Now you add these two. Now this is nothing but m of t. What is m of t finally? Now this is 0, 1, 2, 0, 1, 2. 125.